This is a lesson on the second law of motion in classical Newtonian force analysis. In order to tie ideas together from Newton's first law, we need to explore the ideas of acceleration and net force in order to put them together into a quantitative relationship. And of course, remember, acceleration is the change in velocity of an object, which means we have to consider two aspects. The vector component requires us to consider the magnitude and the direction. So constant acceleration can look like linear acceleration, where we just have a change in the speed. Change in speed. And this can be in one dimension. We only have motion along one dimension, but the speed, the magnitude, that length of that vector is changing. As opposed to the direction, you can have that velocity vector changing direction, which results in motion that is nonlinear, and an ideal example of that is centripetal acceleration, where the velocity vector is changing constantly within a circle, and you can even have a constant speed with some sort of change in path, and that's centripetal acceleration. And we can relate this idea of a change in motion that Newton's first law introduces with net force. What is a net force? And to talk about net force is a vector. And when we talk about net force, we're talking about all of the forces on an object. And remember, vectors are 2D or 3D. We have a lot of forces going on. We'll simplify it to be easier in 1D. But we're going to take all those forces and add them up and say they're causing a change in motion. They're causing an acceleration. And when we consider this, we have to look at external forces as opposed to internal forces. External forces are forces acting on a system from outside the system. And those are the forces that get added in the net force, all of the ones that are external. You can imagine if I have multiple bodies in a system, so I just have two boxes on top of each other here, there's some sort of interaction force between the two. The first one's holding the second one up and the second one's pushing them down. But when I look at the net force on the system, I won't include these internal forces in here, and they would add up to zero, right? Like I would get a force up and a force down, and they end up adding up to zero, and so we just exclude them and only look at external forces. So again, when you're drawing free body diagrams, making sure that you are aware of which forces are external and acting on that body is important. The second law of motion takes everything that we conceptualized in the first law of motion and puts it into an equation for quantitative purposes. And we can see that the acceleration depends on how much force is being applied and also how much mass is there. That's the inertia part. And so if I have a larger net force, if I have more force on that mass changing its motion, it will have a larger acceleration. And that allows us to use these concepts in calculations in order to calculate forces and do a force analysis. Over the years, I've put together a 4-step force analysis strategy for you to be able to follow so that every time you look at a problem, you know how to step through the analysis regardless of what quantities are asked for in the question. You can always do this and know where to start a force analysis problem. Of course, the first thing is to draw a general sketch of the situation, especially if it's not provided. And this allows you to kind of encode the problem, see what's going on, and also evaluate your assumptions. Are you assuming there's motion? Are you assuming there's friction? There are many assumptions that might come out in encoding the general sketch that would have implications for drawing the free body diagram, which is the first important step in here. And it may seem like an extravagance to have a free body diagram. There's already a general sketch of the situation. But what is important about a free body diagram is that you will be using it in order to write equations. It is the tool, the representation of the information that will allow you to formalize quantities into a representation that you can put into an equation. And so a free body diagram to me is the first and most important part of the problem, which is why I put it in step 1. And what you're going to do is draw a free body diagram for each relevant object or system of objects, and I have a lesson on that. First of all, identify all the external forces acting on the free body diagram, and this may seem I don't know, obvious. But what I can tell you is because you're using this representation as a tool for your equations, if you're missing a force or if you have too many forces, this will affect your equations and you will not get the correct answer. So identifying forces and getting this free body diagram accurate is going to be a very important aspect of the whole problem solving process here. Because we're dealing with vectors on your free body diagram, make sure you assign a coordinate system. And my tip here was to put a major axis in the direction of the acceleration, such as the acceleration in the other dimension is 0. That will make your math in algebra easier. And once you do that, you can decompose any forces as you need to within that coordinate system. If there's 2D, you would end up using the two-dimensional version of Newton's second law, which requires you to separate the x components of the motion from the y components of the motion. And if you're familiar with projectile motion, you've already done this sort of analysis where you have different components in different dimensions. If there's one dimension, it's pretty straightforward. Make sure you're taking care of positive and negative signs if they're pointing in different directions according to your coordinate system. Once you get all that written out, notice that I don't have you identify knowns and unknown quantities until this step. You can do all this analysis without knowing any numbers. Once you get those equations, you can look at your knowns and unknowns and know what you're trying to solve for and implement any algebraic techniques you need in order to solve. The bonus step down here, step 5, is reflect on your answer and reflect on your problem-solving strategy. Does your answer make sense? Do the units work out with dimensional analysis? And also, what was the general strategy that was there anything in this problem that you particularly learned about the concept or were needed to sharpen yourself on in order to solve the problem? So reflecting on your problem-solving strategy is important. I've chosen a single problem, moving a trunk, in order to exemplify just basic application of Newton's second law. The problem says, 2 children are moving a very large trunk by sliding it across a rough floor. The trunk's mass is 90 kilograms. And I'm going to draw a general sketch over in the corner here of the situation. There's a trunk, big old trunk. I'll call this MT, and they tell me MT. I'll write this over here, 90 kilograms. This is the mass of the trunk. And I can also write down here that I know the weight of the trunk. It's mass of the trunk times G. That will be a force relevant for our problems later. So there's a trunk, and what I'm going to note is that there's 2 children acting on it. So I know that there's going to be an F1 and an F2 from 2 different children. I don't know any details yet, but I have that going on, and I'm going to have them push it in this direction so it's not getting pushed off the page. It says 1 child pulls on one end of the trunk with a force of 86 newtons, while the second child pushes on the other end with 136 newtons. So I'll write down these quantities here. I know their values, and I'm going to note that 1 pulls on the trunk, and it's going to be a shorter vector than the other child that pushes on a trunk. In some textbooks, the formal free body diagram, when you do this, will have both forces extending from the object on a single side, but I am fine if you represent it with a pull being away from an object and a push being towards an object. I think that makes sense in understanding and encoding the problem. Let's see. This causes the trunk to move at constant speed. Oh, I'm going to note this. Constant speed. Part A says that there's constant speed. Part B says there's acceleration. So I'm going to write for part A that the acceleration, if there's constant speed, the acceleration will be 0. I'll make sure to write that down. This causes the trunk to move. Determine the friction force between the trunk and the floor. So it's getting slowed down by friction, and I'm just going to make a note over here that there's a friction force on this general sketch. And note that this is a general sketch. This isn't the free body diagram yet. I can go ahead and draw a free body diagram. Let's see, I can put it right here. We'll put it below here. There's F1 and F2, and there's also friction. And it's moving at constant speed. When I think about the two forces pushing in one direction and the other force pushing in the other, these two must balance out the other one in order to have an acceleration equal to 0. Our equations will tell that, but I wanted to just draw this vector at a sort of appropriate length in order to get a feel of the problem. There's two more forces on this mass. There's the weight. I mentioned that over in the information here. There is a weight. And to counterbalance the weight so that there's no acceleration in the y direction, there must be some sort of normal force. Fn equals the normal force. And F equals friction, the force of friction. So I've defined all my variables. I don't know the force of friction, and that's what it asked me to find for. Determine the force of friction. So I'm going to assign a coordinate system. I have not done that yet. It's moving to the left here. So I'm just going to make the upward positive and to the left positive just because it's moving in that direction. That makes sense to me. So I have my free body diagram. I've identified all the forces on my free body. I've assigned a coordinate system, and I note that I don't need to decompose any forces in my coordinate system. So I can move on to the second step. The second step of the force analysis says apply Newton's second law. I'm not plugging in any numbers yet. I'm going to apply Newton's second law. So if I apply Newton's second law here, the net force, the sum of forces in the x direction, has to equal max. And it's not accelerating in the x direction. We already said that. All right, so I can write a big 0 on this side. And mathematically, that's true. What goes on over on this side is I'm going to take all the forces, all the vectors that are in the x direction, and add them together. So when I look at this, and this is the forces, that's why we have a free body diagram. The forces on the free body diagram go on this side of the equation. So when I look at the free body diagram, I have F1 and F2 in the positive direction. So I'll go F1 plus F2. And I'm going to note that the force of friction is in the negative direction. This gives me the equation I can use to solve for things. This is the result of applying Newton's second law. It asks me to determine the friction force, so I'm going to solve this equation for the friction force. Force of friction equals F1 plus F2. Well, I know those two values, 86 plus 136. And when it comes down to it, when you run this through your calculator, you get 222 newtons, and that is the frictional force. That is the answer for part A, and we can put a box around it. Part B changes the situation. I noticed before there's an acceleration. Let's read what's going on here. Assume the friction force calculated in the previous part. Okay, so we're going to assume 222 newtons. Now we know it. Both children increased their efforts and caused the trunk to accelerate across the floor at 1.3 meters per second squared. So let me write that down, 1.3 meters per second squared. That's the acceleration in this case. The second child pushes with a force double the pull of the first child. So the push equals 2 times the pull. And I know the pulling force is F1 and the pushing force is F2. So that gives me an equation in order to relate those two forces. That's what that statement means. The second child pushes with a force double the first child. Okay, so I have a relationship, and they ask me find the force each child exerts on the trunk. Well, I'm not exactly sure how to solve for it right now, but I know I need to do a force analysis. So let's write the equations out. I'm going to start with the same form up here. The net force equals ma in the x direction. I know the acceleration now. It's given as a value. I'm going to leave it as a symbol in there for right now until I get done solving. Over on this side, I can write out the forces on the free body diagram. The forces on the free body diagram go on in here. And we're going to note nothing's really changed from the other, except F1 and F2 are larger, it seems like. But otherwise, they are still the same symbols and they're in the same orientation. So I have this equation now to work with. And it seems like if I'm solving for each, I have two unknowns. I don't know F1 and I don't know F2 in this situation. F1 equals question mark and F2 equals question mark. But I have two equations and two unknowns, so I can solve. I'm going to take wherever I see F2 in this equation, I'm going to put 2F1. I'm just going to do a substitution in there. So that gives me this equation, F1 plus 2F1 minus the force of friction equals ma. Well, we can see a factor of 3F1 gathering here. I want to solve for F1, so I'm going to move the force of friction over to the other side, plus the force of friction. And I'm going to solve for F1. F1 equals 1/3 ma plus the force of friction. Now that I've solved for it algebraically, I'm going to plug in values. I have 90 kilograms times the acceleration is 1.3, and then I'm going to add on the 222 newtons. That is the force of friction from the previous problem. When I run this through the calculator, when I add those and then take 1/3 of it, we get 113 newtons. F1 is 113 newtons. Because I know the relationship between F1 and F2, I know that F2 is twice F1, so that's 226 newtons. And that would be the answer for part B on this problem. And just to review, remember to draw a general sketch. Kind of encode that problem into your head, get all the details of the physical situation. Once you get that done, you can draw a free body diagram, assign your coordinate system, and then each part of a problem will have you apply Newton's second law and make sure you're writing this out proper. Get your signs correct, get your acceleration correct, and that will give you equations to be able to solve for numerical values.